I got a permanent magnet alternator, or PMA, from Missouri Wind and Solar, and I wanted to do a video about just the dimensions and things that I had questions on, and I didn't see material available for that, so I just thought I'd quick make a video. This is the way it came. It was in very good packaging. Everything came in very nice. It's based on I believe a 10 SI Delco alternator, and it's been rewired, and the stator has some pretty strong magnets in it. The power comes out in a pigtail here with 3 wires. I like that because then I don't have to hunt around for a connector. I can just solder directly to these. So that's how the electrical connection is handled. For this generator, or for the Delco 10SI, you can go online and get dimensions for the mounting holes, and they are supposed to be 6.6 inches center to center. So if you're wondering what those are, I think 6.6 is a good number. The shaft itself is smooth. There's no keyway on it. And if we measure the diameter, okay, we're looking at 0.67, and this is inches, so I believe that's just under 17 millimeters. I'm using a dial caliper because there's some strong magnetic fields here, and I don't want to booger up my other calipers with this. So that's why I'm using the dial. It's a cheap Chinese indicator. Could be off by a couple thousandths. So take the measurements with a grain of salt. Okay, so the shaft comes out. If we go down to the shoulder, that's just a little inside the housing there. It looks like it's 1.77 or so from this to that shoulder that's there. Okay, so that's the shaft, and the thread. Looks like we've got about, call it 0.6 inches of thread sticking out here. It came with a rectifier, 3-phase rectifier. It's a very nice one. I'm not going to be using it, but it's nice, and I want to hang on to that. Okay, so mounting hardware that comes with it. We've got 3 spacers, 2 of them with a little smaller outer diameter than this one, and that smaller outer diameter allows it to go into this opening of the housing right here. And then we've got a split ring lock washer and a nut that goes on the top. So one of these spacers here is about 200 thousandths thick, and if you put that on here, it's just a little bit over this, just higher than this housing. Let's see if we can get a measurement on that. It's somewhere around 75 thousandths sticking out there. This other spacer is 375, about 3/8 of an inch. That also fits in there, sticks out a little farther. And then you've got a bigger one here. And I believe the thought is that you put these spacers on, you put your pulley on, cap it off with that, stick a split ring lock washer, and then just tighten the whole business down, and that will be what holds it on. I'm not planning on just mounting my windmill directly to this. So what I did was I bought a fan and pulley kit. So I got the fan, and this is the 66 millimeter pulley. So what I decided, I could use the small spacer and that would probably be fine. I went with a bigger spacer. Probably makes it so that it's a little less efficient with the cooling, but I'm not going to be, pulling that many amps through it anyway. So then I can take this pulley. There's one protruding section here. I'm going to put that face down onto there. And then I'm just going to put the lock washer directly onto that. And then tighten this down. So that's how I'm going to mount the fan and the pulley. There's a hex hole here. You can take a standard metric wrench and hold the shaft steady while you tighten the nut. And this wrench is 0.319 or somewhere around there, 0.315 inches, so you can convert that to metric. Another question, want to know how far this pulley is from the surface I'm going to be mounting to, and if that's kind of crude measurement here, but if I just take this, get about midway in the pulley, it looks like it's about an inch from this surface to the center line of this pulley. And of course that's going to vary depending on what spacers you use, but it looks like it's an inch up there. Another big question I had was, is there any cogging? And I would expect some cogging with a permanent magnet and iron core. And yes, there is a little bit of cogging. And so what I'm going to do is I'm going to measure what kind of torque it takes to get this thing going. So I have to make sure that my turbine can generate that kind of torque just to get this thing going. Okay, one thing I didn't mention before, these holes are smooth bore and they're around 390 thousandths in diameter, somewhere around there. Alright, so I have a little lever arm in the generator. I've got this kind of propped up against a board so it doesn't roll. And this is marked at 5 inches out from the center. I've got a cup with some hardware in it and a hook and a little string here. So the idea is to see what it takes to get this to turn. So you can just place the weight at this mark and then see if we get some rotation. So we don't quite have it there. So I'll just add a couple bolts in here, maybe 3. And then we'll see how that does. So just put it on the mark and release. Nothing quite yet. Put a few more screws in there. I'm just trying to sneak up on it. Oh, there it goes. Alright, so we have a 5-inch lever arm. Let's measure this cup here. A little closer in there. Okay, so here we go. And we got, looks like 308 grams at a 5-inch lever arm, and that overcame the cogging torque. So there's going to be a lot of variation, I'm sure, but at least that gives us a ballpark figure of what we're looking at. As far as the cogging torque, we had a moment arm of 5 inches, 308 grams to get it to go. So we convert that to newtons, convert that to meters, and we get 0.38 newton meters cogging torque. Alright, first electrical test. I've got a bit of the pigtail exposed here. Let's just measure stator resistance. And it looks like, yeah, it's probably wiggling a little bit. It throws it off, but let's try the other one. It doesn't look like much. Something like on the neighborhood of 1 to 2 ohms. I have a feeling that any little jiggling is going to show up as a voltage, and that's going to throw the resistance reading off. Let's try it this way. About 1 ohm there. .9 ohms. So we're looking at about a 1 ohm stator resistance, which is quite low. That's good. It means it can handle power. Okay, I'm going to hook it up to the scope, and I'm just taking the hex wrench and turning this. Okay, so you can see kind of what we're getting here as far as waveform. Go a little bit faster. So we're getting a peak-to-peak voltage of around 6 volts at a frequency of about 5 hertz. So that's an approximate thing. If I just do a single sweep, it's showing 5.43 hertz with a 6.2 volt or 6.24 volts peak to peak. So that's an idea of the peak to peak voltage, and yeah, we can convert that to RPM and what sort of peak voltage we can expect. Okay, so we had 6.24 volts peak to peak at 5.43 hertz. So if we convert that hertz to RPM, so it's 5.43 cycles per second, but we had 7 cycles per revolution because there's 7 poles, and multiply by 60 and we get 46.5 RPM. So that's what I was turning it at when we took that measurement. And it's going to be rectified, so we'll just take that peak to peak voltage, divide it by 2, get 3.12 volts. So if I wanted to get up to 14 volts, just to cover 12 volts for the battery and a couple diode drops, this is an approximate value here, we're looking at multiply the 46 RPM divided by the 3.12 volts, and we get 209 RPM. So that's the rotational speed I think it will need in order to start pushing current into the battery. And with a stator resistance of 1 ohm, once it starts pushing it in, it's got plenty to give. So anyhow, I'll just have to make sure I gear my wind turbine accordingly. Alright, so that is the alternator, and the challenge now is to design a wind turbine to drive this. I'm sure it will produce plenty of power. It's just a matter of sizing the turbine and gearing and possibly electronics to make good use of this.